All right, let's start. So welcome to this colloquium by Govindu on his MTech research work. So if there are questions, please unmute and just ask the question directly. And feel free to ask questions during the talk. But if otherwise, keep your mic muted so that there's no disturbance. So Govindu, you can start. Turn on your video also, please.
Yeah, so I turned on. Can you see? 1 second. Yeah.
All right. Okay. Please start.
Yeah. So thank you for attending. Welcome to the talk. So I'll be presenting my work on multi-connectivity for URLLC and coexistence with eMBB in time varying and fading channels. So this is the outline of my talk today. First, I'll introduce about URLLC. Then I'll discuss about multi-connectivity. Then I'll present the system model, followed by our numerical results and conclusions. So before going into URLLC, I'll first speak about 5G use cases. So 5G has broadly 3 use cases. The first one is enhanced mobile broadband, abbreviated as eMBB. It provides services like augmented reality and virtual reality. And these services require data rates in the order of hundreds of Mbps. The second one is massive machine type communications, abbreviated as MMTC. It provides services like smart grid traffic management. In MMTC, the density of the devices is extremely huge. It can be up to 1 million devices per square kilometer. The third one is ultra reliable low latency communications, abbreviated as URLLC. It provides services like factory automation, telesurgery, automated traffic. We can see the 5G triangle here with the 3 use cases. And the key aspects that define these 3 use cases, for example, for eMBB, high data rates and large spectral efficiency. For MMTC, extremely dense coverage and long battery life. For URLLC, high reliability and low latency. Now we'll see much more about URLLC now, its requirements and techniques. So as we saw, the URLLC provides services like telesurgery and factory automation. Therefore, the cost of error in these kind of services is heavy. So the data has to be transmitted with very high reliability. To give you an idea, these are the typical requirements for URLLC. When it comes to reliability, it should be greater than 99.999%. And the data has to be transmitted within 1 millisecond latency. So the data not only has to be transmitted with high reliability, but it also be transmitted in very low latency. To meet those challenging requirements, we need novel techniques. The first one is multi-connectivity for reliability. And the second one is the immediate transmission of the URLC data on mini slot level. Now we'll see in detail about these 2 techniques. First, I'll introduce about multi-connectivity. Before that, to get the language, I'll introduce what is the resource elements of carrier bandwidth and all those. So here we can see it's a time frequency grid. Each rectangle, each grid we see is a resource element. It is one subcarrier during 1 OFDM symbol. The subcarrier bandwidth ranges from 15 kilohertz to 240 kilohertz. In LTE, it is only 15 kilohertz, whereas in NR5G, it can go up to 240 kilohertz. The 12 subcarriers, they constitute a resource block. It's called PRB, physical resource block. And group of PRBs form a subband. So this is the basic definitions of PRB and subband. Now let's see about multi-connectivity. So what is multi-connectivity? In it, multiple base stations transmit the same data. Therefore, the reliability increases because the probability of failure decreases because you're transmitting the same data from all the base stations. There are 2 types of multi-connectivity. First one is called orthogonal transmission, and the second one is joint transmission. We'll see about these 2 transmissions now. So joint transmission, it's abbreviated as JT. In joint transmission, the base stations transmit on the same time and frequency resources. We can see the time frequency grid and the data is getting transmitted on the same time and frequency resources. All the base stations use the same modulation encoding scheme, and the base stations employ maximal ratio transmission. So what is maximal ratio transmission? In it, The signal from each base station gets multiplied by a weight that is proportional to the wireless channel gain between the base station and the user. Here H1 is the wireless channel gain between the base station 1 and the user, so the weight is proportional to the wireless channel gain. As a result, the SNRs add up. We need channel state information to determine the MRT weights because the MRT weights are proportional to the channel gains. So we need channel state information from the user to the base station. Now let's see about orthogonal transmission. So in orthogonal transmission, the base stations transmit on different frequency resources and different base stations can use different MCSs. The successful transmission happens if base station decodes at least one of them. Here the CSI that is fed back from the user to the base station is quantized. So that's a brief introduction about the two types of multi-connectivity, which are orthogonal transmission and joint transmission. Now let's see the second technique, which is to reduce the latency. That's mini slot level scheduling. What is that? Why we need that first? So what is the problem with the slot level scheduling? Let's see this scenario. Let's say the data has arrived here and this is the slot duration and the next slot starts here. In slot level scheduling, the data, even though it arrived much earlier, but it has to wait till the start of the next slot and then only it will be scheduled. Whereas in mini slot level scheduling, what happens is the data arrived here. It will be transmitted on the next immediate mini slot. We can see the latency is ranging from here to here, whereas in mini slot level scheduling, the latency is only this much. Therefore, mini slot level scheduling is needed for latency critical services like URLLC. Now let's see the URLLC eMBB scenario. What happens when you immediately transmit the URLC data? So first thing, the URLC data is sporadic. Therefore, static reservation of resources for URLC leads to wastage because you don't know when the URLC data arrives. So you cannot reserve before only for the URLC data. And we saw the latency requirement for URLC data is critical. Therefore, it cannot wait till the end of ongoing slot. Therefore, the URLC data punctures eMBB data. We see here the time frequency grid. This is the slot duration and this is the mini slot. We saw eMBB users, they have been allocated a chunk of bandwidth and they are transmitting their data. The eMBB URLC data arrived and it punctured on the mini slot level. What happens because of this? The block error rate of the eMBB data increases. Here we see the block error rate with the SNR without puncturing and after puncturing. We can see the block error rate is getting increased. For example, if you see at the same SNR, the block error rate, we can see an increase after puncturing. If block error rate increases, the probability of decoding decreases for the eMBB. As a result, the throughput eMBB throughput decreases. So that's the basic introduction about multi-connectivity and URLLC eMBB coexistence. Now let's see the challenges. What challenges do we need to address in designing a multi-connectivity system? So we saw multi-connectivity increases reliability because we are transmitting from multiple base stations. But at the same time, in the URLLC eMBB coexistence scenario, the eMBB data is punctured at multiple base stations. We saw it is getting punctured. We need to minimize the impact on the eMBB traffic. As the eMBB BLER increases, its throughput decreases. So we need to minimize the loss in throughput for the eMBB. The second one, the frequency selective nature of the wireless channel. In this scenario, the channel varies across subbands. The third one is the time varying nature of the wireless channels. What it causes is we saw CSI is required for both the multi-connectivity types. It becomes partially outdated by the time of transmission. So we need to address these challenges while designing a multi-connectivity and a URLLC eMBB coexistence system. So before going to the system model, I'll just present the summary of the contributions that we have did. So first, we derived insightful expressions for achievability, which is the probability that the URLLC error requirement is met by multi-connectivity. The second one, we propose a low complexity algorithm called multi-connectivity MCS selection algorithm to select the subset of cooperating base station and their MCSs. We propose a novel stochastic reliability constraint for URLLC in time varying channels. So that's the contributions we have made. Now let's see about the system model. So this is the basic system model that we have worked on. There are multiple base stations, set of base stations B, and subset of base stations S serves the URLLC user. For example, here base stations 1, 2, 3, 4, they form the set B, and subset of base stations yes, here 1, 2, 3, they're transmitting to the URLLC user. There is a controller. It is connected to all the base stations. The controller basically determines which base stations to transmit to the URLLC user and what MCS or MCSs they should employ. And we can see eMBB users are connected to one base station. So this is the basic system model. So first, how does MCS is selected in mobile communications? First, the idea is highest rate modulation and coding schemes that satisfies the pre-specified BLER target is selected. For example, we can see the BLER versus SNR curves for different modulation and coding schemes. As the modulation and coding scheme, the rate increases and modulation goes to higher levels. The BLER also decreases for the same SNR. We can see it here. For example, let's take the BLER target to be 10 power minus 1. And these are the threshold SNRs for each MCS such that the block error rate of that MCS is 10 power minus 1. We can see, let's say T1 is a threshold SNR for the first MCS for such that the BLER is 10 power minus 1. Similarly, T5 and T9 are the threshold SNRs for the fifth and ninth MCS similarly. So we can see the MCS M is selected if the SNR lies between the threshold of the mth MCS and it is less than the threshold of the m plus 1th MCS. This is good when gamma is a scalar, which means when the channel is flat fading. But we saw in frequency selective fading, the channel varies across subbands. That means not a single gamma will have vector of SNRs. How do we determine the MCS given the vector of SNRs? So this is the problem. So we have subbands here on frequency. We can see they're experiencing different kinds of SNRs. Subband 1, gamma 1, subband 2, gamma 2, subband n, gamma n. First thing, same MCS to be used on all the subbands. Why? To reduce the control channel overhead. What I mean by this, when a base station is transmitting to the user with a particular MCS, there will be an indicator indicating this MCS is getting used will be indicated to the user. If different MCS, different subbands use different MCSs, then for every subband we have to transmit a control channel indicator indicating the MCS. So to reduce the control channel overhead, it is decided the same MCS should be used in all the subbands. So we have vector of SNRs and we need to select the MCS given this vector of SNRs. To do that, we use a technique called exponential effective SNR mapping. It's a link quality metric. We'll see what it does. So the exponential effective SNR mapping, it converts vector of SNRs into single effective SNR. It is dependent on MCS. For example, this is zeta m is the effective SNR of an MCS M. It is given by this formula. Beta m is an MCS specific constant into log of 1 by n summation 1 to n exponential of minus gamma I by beta m, where gamma I is the SNR of the ith subband. We can see the exponential effective SNR mapping. It is converting a vector of SNRs into a scalar value SNR zeta m. So how do we interpret this effective SNR? So it can be interpreted as follows. Effective SNR, it is an equivalent SNR in an AWGN channel that results in the same BLER as in the frequency selective fading channel. Therefore, now we have converted this problem of vector SNRs into its scalar SNR. So this is how the MCS selection is done for both flat fading and frequency selective fading scenario. Now let's see the go to the URLLC eMBB optimization problem. So what is the goal of the problem? to select the subset of cooperating base stations and their MCSs that minimizes the eMBB throughput loss while satisfying the URLC constraints. We saw we are puncturing the eMBB data, so we have to minimize the eMBB throughput loss. At the same time, we need to satisfy the URLC error constraint. Now, the form of the optimization problem depends upon multi-connectivity mode, whether we are using orthogonal transmission or joint transmission, and the interference setting. At the interference setting is high or low. We saw what is OT and JT multi-connectivity types. Now we'll see these high and low interference settings. What is meant by them? What happens? First thing is high interference setting. So what happens here? Now let's take the case of OT. So we can see this is the OT. Base station 1 transmitting URLC data on subband 1 and base station 2 transmitting URLC data on subband 2. Now base station 1 transmits eMBB data on subband 2. Similarly, base station 2 transmits eMBB data on subband 1. Similarly, base stations 3 and 4, they also transmit eMBB data on those subbands. We can see the packet from the first base station sees interference from all the base stations, remaining base stations, because they are transmitting eMBB data on that subband. Similarly, the packet from base station 2, which is getting transmitted on subband 2, will see the interference from the remaining base stations. So this is the high interference setting. In JT, for example, base station 1 and 2, they're transmitting the data on the subband 1. Here it's only one packet because it's getting transmitted on same time and frequency resources. The packet from the base station 1 and 2 will see interference from base stations 3 and 4. So this is the high interference setting because here the idea is we will puncture only the cooperating set of base stations. Here base station 1 and 2 are the set of cooperating base stations, so we are puncturing only there. What is low interference setting? Same example. In OT, base station 1 is transmitting on subband 1 and base station 2 is transmitting the LC packet on subband 2. Now, to avoid interference to the URLC packet that is getting transmitted on subband 1 from base station 1, base station 2, 3 and 4, they don't transmit anything on subband 1. Similarly, to avoid interference to the packet on the subband 2 that is getting transmitted from base station 2, all the base stations do not transmit anything on the subband 2. So we can see in the low interference setting, the number of eMBB resources that are getting halted is much more higher compared to the high interference setting because we want to avoid interference to the URLC data. In joint transmission, low interference setting is nothing but all the base stations transmitting. For example, here base station 1, 2, 3 and 4, they are all transmitting because all the base stations use the same time and frequency resources. None of them will interfere because all the base stations are transmitting. So this is the introduction about both interference setting. Now we'll see the form of the problem. I'll discuss for JT. So we show it for the high interference setting. So the objective function is to minimize the throughput loss or the subset of base stations S subset to B and MCS belonging to the MCS set. Here LM is the throughput loss at a base station when M is the MCS of the URLC user. Since you're transmitting from S base stations, it is multiplied with cardinality S. Now the constraint is given by this, the block error rate of the MCS M. Since in JT, SNRs add up because of MRT, this is the SNR. J belongs to S. S is the subset of cooperating base stations, summation of gamma J, where gamma J is the SNR of the Jth base station. So this block error rate should be less than the final error target. So this is the optimization problem. So first thing, whether any feasible solution exists or not. What is meant by feasible solution? Whether any MCS or a set of cooperating base station exists such that this constraint is satisfied. So we'll see what is the probability of existing a feasible solution. Before that, here we need to know the block error rate given the SNR. To do that, we'll use a truncated exponential function model. So it's given by this. The block error rate of an MCS M at SNR gamma it will be 1 if it is less than a threshold lambda m. And if it is greater than lambda m, it can be equated with a truncated exponential function. We can see the plot for all the different MCSs, BLER. The circles show the truncated exponential function and the solid line shows the simulated BLER. We can see the truncated exponential function accurately approximates the BLER. It's only valid after if the SNR is greater than a lambda, which we can see here for different MCSs. Now, for frequency selective fading case, we use effective SNR in place of gamma. We saw how effective SNR is computed given the vector of SNRs. So now we know how to compute the block error rate given the SNR. Now let's see the probability of a feasible solution. We'll derive how the probability of existing a feasible solution. We call it achievability, probability a feasible solution exists. Let's take the case of joint, we're dealing with the joint transmission, and for the flat feeding case. It is defined like this: probability such that the block error rate using the lowest MCS and transmitting from all the base stations, J belongs to B, if this block error rate is less than or equal to epsilon naught. Why do we do this? Because when we use the lowest modulation encoding scheme and transmit the data from all the base station, if the block error rate do not satisfy the constraint even for this scenario, then if you use subset of base stations or higher rate MCS, the block error rate will be higher. So that's why we use this expression to compute the probability. Now, first we'll convert this BLER into an expression using the truncated exponential function. After substituting, we get this expression. We saw C1 and D1 are the MCS dependent constant for the lowest MCS, C1 into e power minus D1. This is the SNR less than or equal to epsilon naught. After simplifying, what we get the summation of SNRs should be greater than a certain threshold value such that the feasible solution exists. So we need to know the CDF of the summation of the SNRs. So I'll provide expression for the flat fading case. So it is given by this expression. So here the PT denotes the transmit power and omega square denotes noise power and sigma j square denotes the path loss from the jth base station. So this is the expression for flat fading. Now we'll see how to deal with the frequency selective fading case. First thing, we saw that for achievability, we need the CDF of the summation of SNRs. In frequency selective fading, we have effective SNR. We saw how it is done, how to compute the effective SNR. We need the distribution of that effective SNR. But there is no closed form expressions because of its nonlinear nature. So to solve this problem, we use an approximation which is the term inside the logarithm. For example, this term is approximated with a beta random variable. So as a result, the CDF of the CCDF of the effective SNR can be expressed in terms of the CDF of the Y1. CDF at exponential of minus theta by beta 1, where beta 1 is the MCS specific constant for the lowest MCS. So since it is a beta random variable, its CDF is given by incomplete beta function, which is given in this form. So now this beta function has two parameters called A1 and B1. They are given by these expressions, A1 and B1. Here GJ and SJ, they're functions of transmit power, noise power, and path loss. So once we know the transmit power, noise power, and path loss, we can compute these beta parameters. And once we compute the beta parameters, we can calculate the CDF directly, substituting in the incomplete beta function. So this is the achievability for JT. Now let's see the same achievability for OT. Here the achievability is given by this expression. The idea is same. Instead here we use the product of block error rates because we saw in OT transmission is successful if base station decodes at least one of them. Therefore, the final error rate is the product of individual error rates. We saw that there is no closed form expression for this achievability because of the BLER thresholds. We saw the truncated exponential function is only valid for if it crosses a certain threshold. So we derive a tractable lower bound to it, and we provide the expressions for both flat fading and frequency selective fading. So this is the lower bound for achievability of OT in flat fading. Here this is given by this expression, and C1 and D1 are constants specific to the lowest MCS. This omega square PT, the transmit power, noise power, and path loss. This lambda 1 is the BLER threshold such that the BLER is less than 1 for the lowest MCS. For frequency selective fading, this is the expression. We use the beta approximation that we saw just now for JT, so that the lower bound can be expressed in terms of regularized incomplete beta function. So we saw the achievability expressions for OT and JT. Now we'll see the simulation and the achievability as a function of error target. So this is the simulation setup. We have 4 base stations. It's a 300 cross 300 grid. The base stations are located at the corners of the grid. We plot the achievability averaged over different locations as a function of error target. First, we plotted for both JT and OT includes analysis and simulation. For OT, the analysis is the lower bound. For JT, it is the same as simulation. The analysis matches simulation. The first thing we can see, as the error target increases, as it goes from 10 power minus 8 to 10 power minus 4, the achievability increases. This is because when the error target is higher, the SNR required to meet the error target is also less. Whereas for very low error targets, the SNR required to meet those error targets is high. As a result, the probability of existing a feasible solution is less. We plot it for 2 transmit powers. At higher transmit power, you have higher achievability because you have high SNR. And second thing, we can see the joint transmission achievability is higher than OT for both the transmit powers. At 5 dBm, this is for OT and this is for JT, and 15 dBm also, the achievability is more. But there is a trade-off here. We saw for JT, MRT, we do maximum ratio transmission. For that, we need CSI, whereas OT, the CSI is quantized. Therefore, joint transmission requires more feedback than OT. Now let's see, this is for the effect of interference on achievability for both the OT and JT. So this is the low interference setting, and this is high interference setting. We saw what are they. In the low interference setting, we saw the URLLC packet will be transmitted without any interference. We plot it as a function of transmit power. As transmit power increases, the achievability increases because at higher transmit powers, you have good SNR. We can see first important thing is the joint transmission achievability is same, whereas for orthogonal transmission, the achievability drops significantly. Why? The reason is we saw achievability is getting feasibility. We checked it when all the base stations transmit. And when all the base stations transmit, joint transmission, the URLLC packet sees no interference because all the base stations using same time and frequency resources. Therefore, as a result, the achievability remains same for JT, whereas for OT, it drops significantly. So this is the effect of interference on both the multi-connectivity modes. Now let's see the next thing, which is the effect of multi-connectivity MCS selection algorithm in reducing the eMBB throughput loss. So to benchmark the MCMSA, we show the results for the conventional thing. So in the conventional, all the base stations transmit, whereas for multi-connectivity and for the algorithm, it jointly optimizes the cooperating base stations and their MCSs. We show the results for both low interference and high interference. First basic thing, we can see the throughput loss. On y-axis, it's per PRB in kbps. Here also per PRB in kbps. We can see the throughput loss in the low interference is very high compared to the throughput loss in the high interference. The reason is in the low interference setting, we are stopping the eMBB transmission at many more resources than high interference. We saw because to avoid interference from a base station, all the remaining base stations will halt the transmission, eMBB transmission. Therefore, in the low interference setting, the throughput loss is heavier. But again, there is a trade-off. We saw for orthogonal transmission, the achievability drops significantly at high interference. So it gives a trade-off. Whether if you want a good achievability, then you have to compromise on the eMBB throughput loss. Or if you want to have a moderate achievability, then you can save an eMBB throughput loss. But again, the achievability of the URLC reduces. So that's a trade-off. And the MCMSA reduces the eMBB throughput loss compared to the conventional method. We can see in both the cases. In low interference, conventional and the algorithm are same because we saw low interference is nothing but all the base stations are transmitting. So now we saw the expressions for achievability, and also we saw the effect of algorithm in reducing the eMBB throughput loss. We saw a trade-off between achievability and eMBB throughput loss. Now let's go to the second problem that we have worked on, which is occurs in time varying channels. We'll see what is the problem there, and we'll see what we did to overcome that problem again. So the first thing.
Hi.
Yeah.
I have a question. So in
Yes.
both the cases, in terms of like achievability and throughput loss,
Yes.
so what we see that like OT is like bad compared to JT. So is there any trade-off like when we should use OT than JT thing, JT thing?
So the JT requires more feedback from the user than OT.
Okay, so basically the overhead is more in case of JT than OT, right?
Yes.
Okay, thanks.
Because we do MRT, as a result, the SNRs add up. That's why the joint transmission has more achievability. Finding it will have more feasible solution more often than OT. But again, the trade-off is feedback overhead.
But yeah, thank you.
Yeah. So here is the problem here. We saw the CSI is required. Let's say the CSI report is reported at time t. Packet is getting transmitted at time t plus tau. By the time of transmission, the channel state information might be partially outdated. So what happens as a result, the instantaneous block error rate requirement cannot be met. Because we don't know the instantaneous, the controller don't know the instantaneous SNRs. The CSI information that it has is outdated. So the instantaneous BLER required constraint cannot be met. So it needs to be replaced with a stochastic constraint. So again, the stochastic constraint mode form depends on OT or JT. First, I'll provide the expression for JT. First, what happens in JT? We saw in JT, we do maximal ratio transmission, which the weights are proportional to the channel gains. Now, these channel gains are based on the channel report at time t. Therefore, they'll be outdated. The MRT weights will become outdated by the time of transmission. So let's say this is the SNR at the time of transmission, which comprises the MRT weights which are outdated. So the constraint is given by this expression. We'll see how to interpret this. The probability such that the block error rate of the MCSM, this is the SNR using the MRT weights, outdated weights. The block error rate should be less than epsilon naught given the channel state information at time t. This conditional probability should be greater than a threshold 1 minus delta. And this delta depends upon the use case. The more the delta, the tighter is the constraint. So now how to compute this conditional probability expression? We need to compute the block error rate of an MCS at the time of transmission, given the channel state information at time t. So we'll see the expressions for JT for both flat fading and frequency selective fading. First thing, the SNR at time t plus tau conditioned on SNR at time t is a non-central chi-square random variable. So as a result, the conditional probability can be expressed in terms of Markov Q function. So this Markov Q function is nothing but the CDF of a non-central chi-square random variable. Since the SNR distribution, depending upon the outdated SNR, is non-central chi-square, the probability can be expressed in terms of Markov Q function. The Markov Q function has two parameters, non-centrality parameter and scale parameter. And these scale parameters we can compute using the conditional statistics of the SNR. So now let's see the expression for JT in frequency selective fading case. Again, we will have effective SNR here. So we use the beta approximation, which we did in the negligible feedback delays case. So that the conditional probability here can be expressed in terms of irregularized beta function. Since we are approximating with the beta random variable, we saw it can be expressed in terms of irregularized beta function. It has two parameters, like we saw A1 and B1 in the non-negligible feedback delays case. Here also we'll have parameters to compute, and these parameters can be computed using conditional statistics of the SNR. So now we know, given the CSA feedback at time t, we know how to compute the block error rate of the MCS at time t. What is the probability that it is less than the error target? Now we'll see for the OT. So for OT, this is the constraint. And we have product of block error rates because we saw in orthogonal transmission, the probability of failure will be the product of individual failures. So the constraint is given by this for flat fading, and for frequency selective fading also give expression. The idea is same. The block error rate at the time of transmission should be greater than 1 minus delta. The probability less than error target should be greater than a threshold. So we provide expressions for OT. Here also we do lower bound because of the closed form expression is intractable. So we provide a analytically tractable lower bound expression to compute the conditional probability. So here is the expression for the flat fading case. We saw the statistics of the SNR is non-central chi-square depending upon the SNR at time t. Therefore, it can be expressed in terms of Markov Q function. Similarly, we will see the expression in frequency selective fading case. We can see it can be expressed in terms of regularized incomplete beta function, because the effective SNR is done using the statistics is done using a beta random variable. And again, the parameters, the beta parameters, we compute using the conditional statistics of the SNR. So we know how to compute the conditional probability for both OT and JT. And we also saw for both flat fading and frequency selective fading scenario. Now let's see the effect of this constraint based MCS selection. To show that, I'll present a heat map. First thing, so this is the heat map representing the probabilities. So base station 1, 2, 3, and 4. These are the base stations located at the grids of the square grid, sorry, edges of the square grid. And this is also heat map. This is ignoring feedback delays. That means whatever the channel state information that is fed back at time t, you take that is correct at the time of transmission, whereas the proposed approach considers the feedback delays. So we can see the probability is much more higher in the proposed approach. There is observation here. We can see the probability decreases towards the center of the grid, because at the center of the grid, the path loss is more. Therefore, the choice of MCSs becomes more sensitive to multipath fading. Whereas near the base stations, since the URL seizure is very close to the base station, the path loss is significantly lesser. As a result, the choice of MCS is not that much sensitive compared to the center of the grid. In proposed approach, we can see the probability is at least 93% throughout the grid, because you're selecting MCS like that. We are first computing whether its probability is less than the error target is greater than threshold or not. Therefore, the proposed approach markedly increases the probability. The next thing this is the throughput loss versus delay as a function of normalized feedback delay, which is FD is the Doppler speed and tau is the delay. We can see as the normalized feedback delay increases, the throughput loss per PRB in eMBB for eMBB users increases. We plot it for the two error targets. That's because as the delay increases, the CSI becomes more outdated with increase in the delay. As a result, the base stations has to go for lower rate MCSs for the URLLC user, which increases the eMBB throughput loss for the eMBB user. So that's the function of throughput loss as a delay. So we saw to summarize. So first we took the address the selection of cooperating base stations and rate adaptation. We did discrete rate adaptation, which is nothing but the MCS model and modulation coding scheme, which have discrete rates. And we derived expressions for achievability, which is the probability a feasible solution exists. We did for both the multi-connectivity methods, for both flat fading and frequency-selective fading. And we proposed a low complexity algorithm, multi-connectivity MCS selection algorithm, that selects the subset of base stations and their MCSs. And it also minimizes the eMBB throughput loss compared to the conventional method. And for the time varying channels case, we saw the instantaneous BLER requirement cannot be met. Therefore, we proposed a novel stochastic reliability for the URLLC, and we also saw how to derive the conditional probability for JT and OT in both the fading scenarios. So these are our publications. The first one is accepted at the ICC and that has recently happened. So in the conference, we did for the only joint transmission case, including both the feedback delays case only for joint transmission, whereas we submitted also to the IEEE transactional wireless communications, which includes both OT and JT and all the things that we have seen in this talk. So yeah, so that's it. From any questions I can answer.
Right. Okay, thanks. Any questions? Just 1 second. Right. This. Okay, just hold. Okay. Don't see questions. Just hold on for a minute.
Yes, sir.
I don't see questions. Okay, then yeah, let's stop now. Thanks to all for attending. Yeah, I'll stop the recording now.